Imagine standing on a silent, clear night, watching a streak of light cut across the heavens, and wondering if a solar flare bursting from the sun millions of miles away could somehow trigger a devastating earthquake right beneath your feet. It is a terrifying concept that has circulated across internet forums and social media for years, but what does actual physics tell us about the connection between our star's magnetic outbursts and the tectonic plates resting deep within Earth's mantle? Today, we are tearing down that myth, examining brand new solar tracking hardware going operational in orbit, and checking in on a newly discovered asteroid making a close approach to our celestial doorstep. You're listening to the Daily Space Podcast by Flarient, your daily conversation about space weather, solar activity, and cosmic events. I'm Ollie, and today is Saturday, August 22nd. Let's get into what the sun is doing today. Starting off with our live space weather conditions, things are remarkably calm across the terrestrial magnetosphere today. If you have been looking at our live dashboards over on Flarient, you will notice that our planetary KP index is currently sitting at a peaceful baseline of 0. Over the past 24 hours, the maximum KP value reached just 1.33 during a minor disturbance earlier in the UTC day, but overall, geomagnetic activity is at absolute minimum levels. For those who might be new to space weather metrics, what does a KP index of 0 actually mean in practical terms? Well, the KP index measures geomagnetic activity on a scale from 0 to 9, where anything below 4 represents quiet or unsettled conditions, and 5 or higher marks a geomagnetic storm. A reading of 0 indicates that Earth's magnetic field is in an exceptionally stable state, with almost no magnetic fluctuation detected by ground magnetometers around the globe. Looking at the supplementary indices, the GFZ-HP30 index reflects this exact stability, showing recent 30-minute intervals hovering around 0.33 to 0.67, with an AP equivalent index of just 3. Furthermore, the disturbance storm time, or DST index, is sitting at approximately -10 nanoteslas. The DST index measures the strength of the equatorial ring current surrounding Earth. When a severe coronal mass ejection hits us, energy gets injected into this ring current, driving DST values deep into negative territory, sometimes down to -200 or -300 nanoteslas during historic storms. A value of -10 nanoteslas is virtually nominal background noise, confirming that there is no active energy injection into the ring current at present. Now, what about the solar wind driving these interactions? Data from our orbital monitors indicates that the solar wind speed is currently hovering around 496.8 km per second. While nearly 500 km per second sounds quite rapid to us on Earth, in terms of solar physics, it is a very moderate, cruising speed for interplanetary plasma. More importantly, the solar wind density is extremely low, measuring roughly 1.2 particles per cubic centimeter. When density is that low, the dynamic pressure exerted by the solar wind on our magnetopores is minimal. Additionally, the interplanetary magnetic field's vertical orientation, known as the BZ component, remains predominantly neutral or slightly northward. Why is BZ so critical to watch? Think of BZ like a magnetic lock and key mechanism. If the solar wind's magnetic field points northward, parallel to Earth's magnetic field, the two fields repel each other like matching pole magnets, shielding our atmosphere from energetic particles. But when BZ tilts strongly southward, opposing Earth's field, magnetic reconnection occurs, opening the gate for solar plasma to pour directly into our upper atmosphere. Because BZ is neutral and solar wind density is low, aurora activity globally is currently confined to high polar latitudes with a modest probability of roughly 26%. So, if you are an aurora hunter hoping for vibrant displays tonight at mid-latitudes, you might want to hold off, as the geomagnetic field is resting soundly for now. Moving into today's featured blog analysis, we are diving straight into 4 crucial topics that cut right to the core of solar physics, technology impact, and planetary defense. First up, let's address a question that frequently pops up across public comment threads: do solar flares cause earthquakes? Our recent deep dive article, titled Solar Flares and Earthquakes, Separating Fact from Fiction, takes a rigorous look at the physics to dispel this persistent myth once and for all. It is easy to see why people might draw a theoretical connection in their minds. After all, both solar flares and earthquakes are gigantic releases of energy. However, as the article points out, these two phenomena operate in entirely separate realm of physics and locations. A solar flare is a massive atmospheric and electromagnetic explosion occurring in the sun's corona, driven by the snapping and reconnecting of magnetic field lines. The radiation from a flare travels at the speed of light, reaching Earth in about 8 minutes, where it interacts exclusively with the charged particles of our upper atmosphere, specifically the ionosphere and magnetosphere. An earthquake, on the other hand, is driven entirely by internal terrestrial geological forces. Tectonic plates move across the asthenosphere due to mantle convection, mechanical strain accumulation along fault lines, and internal heat decay deep inside the Earth. The electromagnetic currents induced in Earth's near-space environment by geomagnetic storms are simply far too weak to penetrate tens of kilometers into the solid rock of the crust to trigger structural fault slip. There is zero statistical correlation or physical mechanism linking solar flare timing to seismic events. It is a classic case of correlation being confused with causality, and understanding this boundary helps us focus our monitoring efforts on where solar flares actually exert their real power. And where do solar events exert real-world impacts? That brings us to our second article, Solar Flares Influence Global Power Grid Stability. While the sun cannot shake the solid ground beneath our feet, it can unquestionably disrupt the artificial conducting grid we have built across it. When a coronal mass ejection, or CME, hits Earth's magnetic field, it creates rapid fluctuations in the geomagnetic environment. According to Faraday's law of induction, a changing magnetic field induces an electrical current in any nearby conductor. In modern civilization, those conductors come in the form of thousands of miles of long-distance high-voltage power transmission lines and metallic oil pipelines. These induced currents, known as geomagnetically induced currents or GICs, flow directly into grid infrastructure, where they enter the direct current neutral points of massive power transformers. Because transformers are engineered to process high-voltage alternating current, direct GIC influx causes the magnetic core of the transformer to saturate. This saturation leads to overheating, harmonic distortion, voltage instability, and in severe cases, automated protective relays tripping to prevent catastrophic equipment destruction. We saw this dramatically in March 1989, when a severe geomagnetic storm collapsed the Hydro-Quebec power grid in Canada within 90 seconds, leaving 6 million people without power for 9 hours. Grid operators today utilize real-time space weather forecasts from systems like Flarient to reroute power, lower load capacities, and protect high-value transformers whenever high KP warnings are issued. Shifting gears from high-voltage electrical engineering to celestial mechanics, our third article clarifies a fundamental astronomy question that confuses many newcomers. Asteroids are distinctly larger than meteors. People often use terms like asteroid, meteoroid, meteor, and meteorite interchangeably, but astronomer precision here is vital. An asteroid is a substantial body composed of rock or metal, orbiting the Sun directly in space, ranging in scale from a few meters across to hundreds of kilometers wide, like Ceres or Vesta. A meteoroid is simply a smaller fragment of rock or dust drifting through space, often broken off from asteroids or comets. When a meteoroid impacts Earth's atmosphere at extreme hypervelocities, typically between 11 and 72 kilometers per second, the atmospheric friction creates intense heat, causing the air around the object to glow. That streak of light flash across the night sky is the meteor, often called a shooting star. Most meteors burn up entirely miles above the ground because the original meteoroid was no bigger than a grain of sand or a pebble. If any solid piece manages to survive the fiery atmospheric transit and strikes the Earth's surface, the remaining fragment is classified as a meteorite. So, to summarize, an asteroid is a mountain in space, a meteoroid is a drifting pebble in space, a meteor is the streak of light in our sky, and a meteorite is the rock sitting on the ground. Knowing the scale difference reminds us why space agencies like NASA's CNEOS focus their tracking telescopes on large asteroids rather than tiny meteoroids. Finally, our fourth article addresses an essential topic for radio operators and aviation navigators: how the solar cycle dictates radio communication conditions. Global high-frequency shortwave radio communications rely almost entirely on the ionosphere, a layer of Earth's atmosphere ionized by solar ultraviolet and X-ray radiation. During the solar maximum phase of the 11-year solar cycle, such as the peak conditions we are experiencing in solar cycle 25, elevated solar flux increases the electron density in the upper ionospheric D, E, and F layers. This heightened ionization enables higher frequency radio waves to bounce or refract off the ionosphere, allowing signals to skip across oceans and continents with incredible clarity. However, it is a double-edged sword. When a strong M-class or X-class solar flare fires off, sudden ionospheric disturbances cause extreme ionization in the low-altitude D layer, absorbing high-frequency signals instead of reflecting them, leading to total radio blackouts on the sunlit side of Earth. Amateur radio operators and maritime traffic monitor daily solar flux numbers and space weather reports closely to predict whether shortwave propagation will offer crystal-clear transoceanic communication or complete radio silence on any given afternoon. Turning now to current space events making headlines today, we have an exciting blend of planetary flybys and major technological upgrades in orbital space weather tracking. First on the astronomical calendar is the close approach of the near-Earth asteroid designated 2026 PX. Discovered earlier this year, asteroid 2026 PX is making its predicted pass by Earth today. Planetary defense networks have calculated its trajectory with high precision, confirming that while it is making a notable close approach in astronomical terms, it poses absolutely no risk of collision with Earth. Flybys like 2026 PX serve as valuable real-world exercises for optical observatories and planetary radar arrays like Goldstone, allowing astronomers to refine orbital modeling, measure surface composition, and practice tracking techniques for future asteroid detection. At the same time, sky watchers in clear northern locations are catching the tail-end remnants of the annual Perseid meteor shower. While the peak occurred a couple of weeks ago, a few lingering icy dust fragments from Comet Swift-Tuttle continue to vaporize upon hitting Earth's upper atmosphere, putting on a faint show for patient late-night stargazers. Now, let's pivot to a major technical milestone that took place yesterday, August 21, 2026, which drastically enhances our ability to monitor these solar events in real time. The National Oceanic and Atmospheric Administration, NOAA, officially brought its brand new Solar 1 CCOR-2 instrument into full operational status. What is CCOR-2 and why is this such a huge leap forward for space weather forecasting? CCOR stands for Compact Coronagraph. A coronagraph is a specialized space telescope designed to block out the overwhelming direct glare of the sun's bright disk using a central occulting disk, simulating an artificial total solar eclipse. By blotting out the core light of the sun, the instrument can capture high-resolution images of the surrounding, faint solar corona. This allows scientists to see plasma clouds and coronal mass ejections the moment they explode off the solar surface and race outward into interplanetary space. For decades, space weather forecasters have relied heavily on aging space instruments like the LASCO Coronagraph aboard the SOHO spacecraft, launched way back in 1995. The activation of CCOR-2 on the Solar 1 platform provides a state-of-the-art, continuous high-definition feed of solar coronal activity with far lower latency. This means that when a major CME erupts toward Earth, forecasters can instantly calculate its expanding speed, directional trajectory, and volumetric density far faster and with greater mathematical accuracy than ever before. It provides a crucial early warning window for power grid operators, satellite flight controllers, and airline dispatchers to take protective measures hours before the plasma cloud strikes our magnetosphere. Next up, it is time for our fact-check segment, where we tackle widespread space conspiracy theories, viral urban legends, and online misinformation using verified scientific evidence. Today, we are taking on a claim that has been floating around internet culture since the late 1990s. The claim, there is a 13,000-year-old alien spacecraft, known as the Black Knight satellite, secretly orbiting Earth in a polar trajectory, and global space agencies like NASA are actively covering up its existence. Verdict: false. Let's unpack where this myth came from and what the official photographic evidence actually shows. That Black Knight legend is essentially a Frankenstein myth, an amalgamation of completely unrelated historical events, misidentified space junk, and fringe science fiction stitched together over several decades. The myth claims origins going back to Nikola Tesla hearing unusual radio signals in 1899, or long-delayed echo radio experiments in the 1920s. However, the specific visual centerpiece of the conspiracy theory rests on famous NASA photographs taken during the Space Shuttle Endeavour mission, STS-88, in December 1998. During that mission, which was the very first shuttle mission to begin assembling the International Space Station, astronauts Jerry Ross and James Newman were conducting a spacewalk to attach the American Unity node to the Russian Zarya module. While working outside, a thermal insulation blanket accidentally drifted away from astronaut Jerry Ross's tether setup. The blanket, designed to shield trunnion pins from extreme temperature fluctuations, drifted out into orbit, where astronaut teams photographed it as it receded into the distance. That thermal blanket was catalogued by NOAA as space debris item number 25544 and eventually re-entered Earth's atmosphere, burning up harmlessly a few days later. However, low-resolution versions of those mission photos began circulating online, showing an oddly shaped, dark object framed against the blue curve of Earth. Conspiracy theorists seized upon these images, claiming the object was an ancient extraterrestrial probe monitoring humanity. Neither NASA, NORAD, the Department of Defense, nor any independent astronomical observatory on Earth has ever found evidence of a 13,000-year-old alien craft orbiting our planet. The object photographed during STS-88 was conclusively a piece of thermal insulation material lost during a routine spacewalk. The narrative surrounding the Black Knight satellite is a classic demonstration of how mundane space debris can be transformed into viral pseudoscience when isolated from historical and technical context. Bringing everything together in our daily brief highlight for today, August 22, 2026, we are witnessing a powerful convergence of operational upgrades and steady astronomical routine. The full commissioning of the Solar One CCOR2 Coronagraph platform provides the precise monitoring tools needed to safeguard our technology as Solar Cycle 25 continues its journey. With Asteroid 2026PX passing safely through our local neighborhood, and space weather metrics holding at quiet baseline levels, we enjoy a welcome period of calm. Looking ahead at the next 72 hours, the Space Weather Prediction Center forecast suggests that interplanetary conditions will remain predominantly stable. Solar wind speeds are expected to slowly decline from their current near 500 km/s levels back toward a quiet baseline below 400 km per second. With density remaining low and no Earth-directed CMEs detected in recent observations, geomagnetic storming is not anticipated over the next 3 days. The KP index is forecast to remain predominantly between 0 and 2, keeping aurora activity confined to high Arctic latitudes. Satellite operators can operate without immediate concern for atmospheric drag spikes, and power grid companies can maintain routine maintenance schedules. However, as sunspot regions continue to rotate across the solar disk, the new CCOR2 system stands ready as our frontline warning sensor should a sudden flare or CME erupt. Before we wrap up today's episode, here are a few quick call to actions to keep you connected with everything happening in the cosmos. First, make sure to visit flarient.com for live space weather data, real-time KP index tracking, high-definition aurora forecasts, and interactive solar dashboards. flarient.com is the official website of Flarient and the absolute best place to see what our star is doing right now. Don't forget to subscribe to the Daily Space Podcast on your favorite podcast platform so you never miss a single daily episode. You can also visit flarient.com/podcast to access our complete episode archives, detailed transcriptions, and comprehensive show notes. Be sure to follow Flarient across social media for instant, real-time space weather alerts whenever solar flares or coronal mass ejections break out. Join the growing Flarient community to connect with fellow aurora chasers, amateur radio operators, and space weather enthusiasts around the globe. And finally, download the Flarient app on your smartphone to receive push notifications directly to your lock screen the moment geomagnetic storms strike. Thank you for spending your time with me today. Keep your eyes on the skies, and I'll talk to you again tomorrow.